Okay, so let me walk you through what we're doing here. So this is my old-timey Variac going to old reliable 150 amp 14 volt transformer. We've got our leads going down to our tube socket. That's going to our tube. Okay. We have our leads here attached to our filament, attached here. This is our amp clamp, and then this is a meg meter that'll allow me to test the insulation value of this tube up to 1,000 volts by pressing that button. If we see anything other than 1 on that meter, we have a leak. All right. This will not tell us grid emissions of the tube. It's not going to tell us output potential. It's not going to, none of that shit. The only thing I'm looking at is to make sure the seal for the tube is still intact. Okay. So first we're going to bring the tube up. We're going to bring it up to 7.5 volts. That'll be shown here. And we're looking for something below like 52 to 54 amps. Anything below that, that's a really good sign. And then we'll kill the light, and then we're going to look at the jade, the ceramic material, and see that it is a white pinkish color and that it's universally lit. Because if the filament, I've had them where the filament's been broken and like literally this half of the tube is lit and the other half is dark, right? And then we'll hit it with some high voltage. So let's go over here, put my hand on the Variac as you guys can see, and we'll start turning the knob. There's 1 volt, 2 volts, 3 volts, 30 amps, wow, okay. 5 volts, 6 volts, 7 volts. Ooh, too high. $7.512, 49.1 amps. It's good. So if this voltage was to unload and take off and go up, and the amp draw to go way down, or for the amp draw to jump way up and the volts drop way off, that would tell me that there's a break in the filament on the inside and that it's shorted. So let's go ahead, let's kill the lights. And as we can see, it's universally white. The camera looks a little pink. Here, let me turn the gain up on the camera. But it's universal, so that tells me that the whole filament structure is lighting up and boiling off electrons like they're free. But they're not. It costs money. Just saying. Okay. Let's turn the lights back on. Now let's do this test here. Ready? The way we have this hooked up is to the anode and to the ground ring of the tube. So we know that there's no hard shorts between the anode and the ground ring, which makes me very, very, very happy. Very happy. And this is actually dropping off a little bit. Sorry, I just kicked the camera, I apologize. This is actually dropping off a little bit as the tube is warming up. We can see our voltage is starting to climb up a little bit as the load's coming off. So we'll go ahead and we'll back this down just a hair. And that looks good to me. Go ahead and we'll shut this off. And now I gotta wait for 10 minutes for enough air to get across the anode of this tube to cool it off before I can touch it. Yeah, that's a win. It's acting like it's new. I was very concerned. I'm not too worried about anything else right now with this tube, other than it didn't have a leak in it. This is like an air bottle test, right? That I do with the 3500Z. You know, turn it on, let it light up, see if the internal structure of the tube disintegrates because there's no vacuum. Same principle here. I want to see the filament volts come up, the amperage come up and stay steady, and then it be isolated with this. So, yay. Man, that makes me happy. Okay, so let's jump back over to the bottom side of the RF deck here real quick. So, Going by math and experience, I can tell you right now, I've got 9 diodes, 10A10s in here. I built this little cute stand for it. It's made on an aluminum piece of 90-degree angle. I got 0.01s, and really all that does is to help throw the wire out of resonance, to keep the RF from coupling from the filament choke and the input RF, keep that from coupling over to the diode string and being able to couple back to the filament transformer and have access to the cathode. So I bet money that this will get us somewhere, these 9 diodes will get us somewhere about 3.75 to 3.5 milliamps worth of current at 0 signal idle. So what I mean by that is amp on, no RF going in, step our foot on the foot pedal and bring the bias on board. It'll take us from cutoff, which is provided by this resistor here, which is a 10K, which still allows us a little bit reference to ground until we turn the tube on by letting it have reference to the center tap of the transformer. I just did order the $95 part, but this will allow us to continue forward. At a minimum, we've got this in here, and in my opinion, this works better. My 40,000, my 15, my 10, my 20, my 6, and my 3,000 are all biased like this, and I can't tell you, every 3,000 I built has got 9 to 15 diodes in it for the bias. Just like this, and they work fine. But me wanting to keep this as a mint restoration, I created this so I wouldn't be stuck for a couple days. And if it works really good, we might leave it in here, but I doubt it. I'll probably rip it all apart and put the actual diode in here that they suggest, which obviously failed. Of course, it helps if you don't put it in backwards. All right, so got the tube somewhat tested. The RF deck looks like it's all in top shape. Now it's time for us to go start working and spending a little bit of time on the power supply. Okay, so our first thing that we got to look at is our breaker. So this arm has been broke off and was broke off long before it showed up into my world. So if you try to cycle this by itself, it'll stay, but it doesn't take anything to trip it. And really, that won't stay engaged unless this arm comes up with it at the same time. So I've got to take this breaker out and install this breaker. I think that's the same. They sure look the same. Same width, same opening. This is a 20 amp. I don't know what this is. Huh. Well, there you go. It's a 50. And it looks like this has been arced out. That's no good. What did this arc out against? Did this guy try to close this panel? Yes. Okay. So somebody's tried to close this panel at some point in the life of this amp. Where's that box of contactors? Nope, not this one. Not this one either. This is a single pole one. This is the one that's melted. At some point or another, somebody has closed that panel with it plugged in, and they've made contact with the bottom side of the coil. So, okay. If that's the case, it might have straight up whacked off the soft start circuit. Okay, that coil's good. Am I in frame? kind of here. That coil's good. And they're using a resistor as a soft start. So I hope that when they dumped 110 volts on this lead and it shorted out, this bottom lead that's on this contactor, this one here, and you can see when the cabinet got closed, there's only like maybe that much clearance between the bottom of the breaker and the contactor, that this wire goes directly to chassis ground. As far as it running back, and I don't know, I don't think so. I really don't think so. Man, that vacuum relay that's in there is expensive. Okay, I guess I need to take a file and I need to cut all this burn that's on here off. Maybe I can zoom in there enough and you guys can see what I'm talking about. See that? See how the whole top of this is royally effed off? I don't think the breaker's bad, but the armatures on the front are broke off. Oh. Yeah, interesting. And these have been replaced. This stuff's been replaced. So, needless to say, these have been replaced. And these are what we got. I got all three of these contactors. Brand new replacement for this one. Brand new replacement for this one. And then this here, and I believe this is our soft start. No. This goes down and it controls over to there. This goes here, so it comes out of here. Yes. It's our contactor that closes it, allows this one to fire. But this is our bleeder bank here, and that's our soft start. Now, there is another little power supply that's down in here, and it's not looking too hot. Let me show you that. Sorry, let me take this back. So our mains come in here on these leads. They come in, they go through our breaker, and then they come out on these leads here, which come around, they come up to these two contactors right here. So then this contactor will close, and the output of this relay will come around, and it goes to this contactor, and the output for it is here. When he changed this out, did he put it back together backwards? So how this should work is there should be a timer someplace, or a circuit that's looking for some kind of reference voltage and based off of time and current draw, and this contactor will close. Because right now this lead's jumpered to here, and this lead is jumpered to here. This should be over here. And this is what closes the second side of the single phase, the other leg of it. That's wired wrong. Right now the way it's set up is 100% of the schmooze going through this wire. These leads run off and they run this little secondary supply that's back here. You guys can barely see it. Here, let me show you this from straight on. You see how they're crossing? So that's one leg and that's the other leg, and it comes in, this comes down. This should come over to this contactor, this side of the contactor. Instead, he's got this leg crossed over and this leg crossed over. For that to work, these have to be equal in size. This wire and this wire. You can see where these close, this closes, and this trips to this wire, which sends the 220 volts up to the head unit, the control interface. And the control interface sends a signal back down. This here, I think that doesn't run the coil, does it? Yes, it does. This runs the coil, and then this opens, and then this closes here, chink, chinkladera, and then this fires this coil, and this goes to ground. And that's what causes this contactor to close. But this isn't wired right. This needs to be flipped around for sure. I bet you anything that this wire here takes off. It runs up to the RF DAC, or the control head unit, and that's what says, hey, secondary contactor's closed, we're good to operate. So the soft starts come into operation. But this don't add up to me. So these are 12 volt mercury. These are mercury grade contactors made by the MDI Corporation in Minnesota. But the coils are 12 volt. 12 volt we got. So let's check. Let's check this contactor. We have it shorted, well, we got our test leads across this. So the top one's ground, we're gonna go grab the bottom one here. Okay, that looks good. Grab our bottom one. Okay. So that looks good. Now we're going to disconnect the top phase here on this contactor. Let's see, bottom one's ground on this one because somebody's dyslexic. That's good. So that looks good too. Let's see, how do I grab this one? And grab it here on that, and grab this. That contactor should be closed, or open, I mean. Motion up. So here's the output. That's our ground lead. Okay, so if this goes here, means I need to grab this here. Yeah. God damn, what a dummy. Okay. I took it out because the way it was wired was upside down and backwards in my mind. But watch. It's like engage, wait. Engage, wait. To me, that's very funny. How this works is there's a little ball of mercury inside this contactor. This is the one that came out of the amp, by the way. This is the backup one. Now, I know in theory you should only store these upright. And once it's laid, it's like a fridge. Once it's laid down, you're gonna give it some time to let all the mercury settle, blah, 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 blah. I know. He had this wired completely wrong. See, where did it go? Now I know where this... I might have finally pitched it. Pushing around the workbench for like a week. One of these set Ellens I've had floating around on the workbench because it fell out of the box. I got plenty of extras, it doesn't matter. So this contactor is working appropriately. This one here. This is 35 amp rated, 240 volts at 35 amps. Yeah, 12 volt DC. 12 volt DC. I don't understand why you'd have the other contactor wired the way he did. Doesn't make any sense. Oh well. Well, let's wire it around so it's right, I guess. I hope this comes out. Okay, so up here at the top, we have our 230 volt single phase comes in. This is our common case ground. This is one leg, and this is the second leg of the 220 coming in. Comes in, goes through our breaker, like we discussed, and it comes out of our distribution bus, and it goes up to these contactors. Okay? One leg you can see continues through, and it goes over, and this is our high voltage supply right here. All of this. So this is our transformer, and these are our tap changes on our transformer, and this is what goes through the vacuum relay that's in there. So we have a resistor that allows us to have our soft start, the R602, which is a 50 ohm, 100 watt wire wound resistor. A little bit high, in my opinion, but what do I know? I'm not an engineer at Henry. Off of this phase, or this leg of the single phase, on pin 3, we have this wire that continues around, goes through a fuse, comes out, comes down, and it goes to this little small supply. That's the one that I was telling you that doesn't look so hot, this one here. This is what runs all of our relays. Okay. After this second contactor fires, right here, we have a tap that comes out, goes through the second fuse, and it comes around, and this is what supplies the RF DAC. Or pardon me, before it goes through this contactor, right here, it taps off, runs down, and that's what runs off and runs our remote head unit. Okay? So this is the other leg of that transformer. This is the output, our rectifier full bridge. And then we've got a capacitor, another resistor for reference. And then this is also what drives our AC main light that's on the front that turns on. It says the mains are on. And then this goes up, relay voltage. Okay? And then that hooks back and comes back in, and that's what drives these contactors. 230 volts out, directly untapped, unfused, everything right here. Goes right out. So then we have a 115 volt reference, and then our filament controls all come from outside the power supply. Let that sink in for a second. So resistor, this is our whole bleeder bank. These 4 resistors. This is our MOV. This is a suppression device. Right now we're focused on this. This is the single contactor that sits by itself. Very low current is what goes through here. That's what we're discussing here. And he had this wired upside down. So basically backwards. He had this lead wired to this lead and this lead wired to this lead, but in reverse. This is our high volt return. This is what drives everything. So the high volt on comes on, resistor, another little transformer, and then out to drive our sideband CW switches, which then in turn drive this switch. Okay. This is wired all wrong. He has this wire here and this wire here, and that's why it won't turn on. He's got these two wires reversed. So when he put it back together after he blew up this contactor, I'd almost bet this contactor or this contactor, when he switched them out, he flip-flopped these two wires. So as you can see, this is unswitched. This voltage here is completely unswitched. This is on the switch side of things from the relay. Okay, just goes off and says, hey, we've got shmoo. This can't be over here. This wire can't be placed on this connection, and this connection can't be placed here. That would mean this power supply is going to be on all the time. And we don't want that. We want this to be tripped so it'll drive the contactors in sequence. This wire and this wire are flip-flopped. That's what I was chuckling about when I said, man, this guy, dummy. I don't know who did this. I don't really care. I find this hilarious a little bit to myself in a lot of different ways. Walk over here. Yeah. It's got freaking wired backwards. Okay, let me change some stuff around. Let's see if we can get this fixed here real quick. Okay, so we went ahead and rebuilt the 28 volt power supply. The old one that I took out, I rebuilt it and put it back into stock for a backup. And now we got to go look at this resistor here. As we can see, if I can get this in frame, turn the brightness up here. As we can see, there's no insulator on the top or the bottom of this. It's just pinched with the screw. That's a no good. So I've got myself some very thin porcelain insulators. I'm going to slip one down on the bottom. And then I happen to have one of these fiber insulators, which is period correct. I'm going to put that on the top. So I pull this resistor out, check it, make sure it's not shorted or burnt. And we'll get this put together real quick. So we did this. I just had to break it down one wire at a time. What we did is we got rid of all the 7mm. And I always thought people were pulling my leg when they told me this, but it says it printed right on the label, spark plug wire. Spark plug wire, 7mm. I always thought people were pulling my leg. Well, I took my Henry 8K apart and I pulled all the spark plug wire out of it. So we replaced it with 15,000 volt neon sign, you know, high voltage silicone boot, soft, flexible, new, no cracks in it like some of the stuff that I found that I pulled out of here. That would have caused all kinds of problems. I think something got dropped in this amp at one point or another on this cap, because the cap's got a little dimple in the lid. The cap's testing fine, it high potted and everything, so I don't know. I don't know, but needless to say, we're at the more than halfway around point at this point. I'm going to put this runner in. I left it out so it wouldn't be blocking our view. I'm going to put this runner in, then the RF deck goes in, and I'm going to leave the tube out for right now. And then I'm going to hook up all the electricals to the RF deck, and we're going to hook up the control head. Fingers crossed. We're going to power it up and see what happens. We'll see if we get high voltage out of it. We'll see if all of our metering works, our lights on the front of the control deck and all that kind of stuff. So let me get the RF deck in. Let me get everything hooked back up. This BNC, which carries all the input watts, which is silly to me that it's on a BNC, but that BNC is looking a little scotty, so I'm probably going to rebuild that BNC too while we're at it. But this took hours. This is no small task. These are all crimped, soldered, and heat shrunk, right? So hours. And then I changed that one resistor down there in the corner I was showing you. There's another resistor that's up on the wall, and I noticed there's a little diode that was attached to the bottom of that resistor up against the wall, and that diode was blown too. So if you're looking for any kind of input help, that has part of the metering, as part of the metering circuit for the high voltage, and that diode was wide open. So it's 1000 volt, like half amp diode. Replace the diode, replace the capacitor. But I think, actually I know. Let's go ahead, let's put the RF deck in this. I'm ready to move forward. Gentlemen, we've got good news, we got some interesting news. So now our filament volts are going to sit too high because there's no tube in the RF deck, but what we got going on is blower motors, all that kind of stuff. I've got it currently set in manual, so we're going to watch this chain here. You move it back. Now we're going to look at this chain here. Okay, now back over here. So technically, we've got most of this working. Most. There's some little things I've got to change, like look into the watt meter. I don't know if our voltage is too high or what. We'll figure that out here in a minute. All the memory pre-selects are working. I've still got to figure this out. This is supposed to go in and stay in, and then I press on it and it comes back, you know, go in, click in, stay in, then press on it, comes back out. That's not happening. So here's the problem. Let me show you what I've got going on. Let's go ahead and we'll shut this down. Let's slide over to the computer. Okay, so this is our relay control supply. None of this works the way I thought it was going to work, right? So we're going to look at this line right here, number 6. This is a white and yellow wire that comes in on my amp. Come to find out, there's many different iterations of this amplifier, and they're all a little bit more bespoke and special. But this is our primary conversation piece that we're having right now. So let me bring a camera over here. Let's pan over to the camera real quick. So my yellow and white wire come in here. This is the yellow and white wire that come in and they feed these contactors. We had this whole conversation just a couple segments ago. Come to find out, none of this works the way I thought it did. So on the other side of this wire is a supposedly 25 ohm 100 watt resistor. It has an unregulated 33.5 volts that I receive from the head unit to turn everything on. So to actually turn everything on, there's one wire down here, specifically that one, pulls 110 volts and sends it up to the RF deck, and then that's what powers up the power switch, and then that in turn lights another supply, and then it dumps 36 volts down. It goes through a resistor to knock it down for these 12 volt mercury contactors, and then on the other side of these contactors there's 2 leads, and that's what runs the 220 volts up to the RF deck and allows us to turn on the power supply in the RF deck. That's how it's wired. So then the RF deck gets its voltage and everything lights up, and for us to turn on the high voltage supply, this is where it breaks from what I think it should be wired like to what the schematic says. Let's go over and take a look at the schematic. So according to the schematic, now we're looking at specifically these parts here and this part here. So here's our 2 primary contactors. Back over to the amplifier. This is our primary contactor. Okay, both poles. Both poles of the single phase. That's our primary contactor. Back over to the computer. Here's our contactor. And as you can see, they're run off the same power supply line. And it's showing, this contactor here is driven by this one here, and it's showing that I have this R603, 25 ohm, 10 watt resistor, okay? Now it's showing for this contactor, let's go back over here to the amplifier. This contactor here fires this contactor here, which off of this wire here and this wire here is what goes to our bypass resistor, which is up in here. Okay? So these two are shown by this one. And let me show you. Let's go back over to the computer. So we have this single contactor represents this connection here. Well, we actually know in reality what that makes up is two separate contactors, which doesn't make any sense. This system here, which I was assuming was this actually is what runs, this here is what actually runs the vacuum switch, which we have control of that. Back over to the amplifier. Let me show you what I mean. So we have control of that over here. This is supposedly our soft start circuit here. Okay. Back over to the computer. You see how this R604? Let's go here, R604. Wire wound, 75 ohm, 10 watt resistor. Back over to the amplifier. I assumed that's what this resistor is. No, this is somebody else's wiring. Somebody else's wiring. Now, I noticed in this amp, there's been some blue terminals that have been added. These are slightly different than these terminals, let's say down here on this distribution strip. I think this whole thing has been rewired because somebody else has been trying to figure out why it wouldn't turn on. Okay, now, I put power to the thing and it won't turn on for me. Literally, these lights will turn on, but the amp won't turn on. Well, I get to digging, and this little resistor, which tested good just a minute ago, I put it in line. Now this thing is completely open. It does nothing. It's bad, right? So, going back to our schematic, let's go back over to the computer. That would be this resistor here, right here. Yeah, was it R603. 25 ohm, 25 watt. Okay. So, I've exported this both ways. Here's a 25 ohm, 25 watt Ormite. I put that in. And boom, now we can turn the thing on. Here's the problem. Let's go over to the amplifier. This lead that comes from this resistor bank I've installed over here is not regulated. And as the current goes up, because we're using a resistor to drop the voltage down from 33 volts, when I go and I tie in the second contactor, now it drops from this one contactor by itself, we'll say is 12.5 volts. When I tie in the second contactor, because the load is thus that it adds more current to the circuit and the resistor can only pass so much current, or pardon me, so much voltage, now we drop down to 8.5. And so then this contactor closes and it fires this contactor here, which is to close the soft start circuit. Remember, this is not shown in the schematic whatsoever. This doesn't exist. This contactor is not in the circuit on the schematic. When this one fires, it drops it down to 5 volts. So then, okay, let's go back over to the schematic diagram. This resistor here and this resistor here, this one doesn't exist. This whole wire doesn't exist. This whole circuit is standing completely outside of this diagram, right? This whole portion of the circuit is completely wired differently on this amplifier. So the only thing that's true on my amplifier is this wire coming in, this resistor, and this contactor. So, okay, let's go up and let's go take a look at the 230 volt two-phase 3K power supply. And now look at how this changes. Resistor, contactor, resistor, contactor, resistor, contactor. So then that made me think, do we have a 3K power supply with an 8K head somehow? Or no, we have an 8K power supply, but it's wired more like the 3K version. So I need to have not one, but two, but three resistors. Let's go back over to the amplifier. If that is the case, where are the resistors? I don't see the wires. I don't see the mounting hardware. I don't see anything in the harness. There's no evidence of this. So how did this work? That's my $6 million question. That's the dilemma that I'm at right now. I want to make this work as most true to when it was manufactured as possible. So, back over to the computer. I have an option. I can do a system like this, or I can do this system here. This system here, if I use this resistor, I'll end up putting like 18 volts on the first contactor, then the second contactor will pull it down to 14, and the third will pull it down to, let's say, 12. And it all happened instantly, and we need to have a soft start circuit. That's what this resistor, let's see, right here is doing. This soft start right here. Well, if I tie all these on the same peg, bam, 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 these all close at the same time. So I might have to do some modifications. Just a hot skippity minute. Let's slide back over to the amplifier. Just a little tiny bit of modification. So let's talk about our options for modification here. Because the end goal is I got to make the amplifier work, right? I've had this whole wire loom apart. I've looked at every single thing in here. I had a couple wires that were cut and they were burned and abandoned. I'm telling you, when this guy closed this lid and shorted against that pole of that contactor, it wiped out everything attached to it. Thank God for this resistor that was popped, because this is what kept it from backing up and blowing up stuff in the RF deck. Okay, so I have a couple choices. I can take and add 3 of these resistors, bring the 35 volt supply, which is this mess over here in the corner. I can bypass the splice where they've got this single resistor, which will never carry enough current to run this whole thing. It won't. So I'm a little perplexed. I'm like, how did they have this wired? I wish I could have seen it before this all got changed and modified and wires got moved around. You don't know how bad I wish I could have seen this before wires all got moved around, right? I can add 1 resistor for each contactor and keep this soft start circuit in play and utilize the full potential of the 35 volt system. Now, if I wanted to hide everything and be a tricky dick, and I might still do this, is there's a big open space right on the back side of these contactors on the other side of this wall. And I take something like this. This is a DC to DC buck converter regulator. This particular one happens to work between 17 and 65 volts. You put 17 to 65 volts in on this lead, you will get 12 volts at 10 amps out. And that comes out on this lead, and then if you needed to, you can split the grounds. Like if they had a different ground reference, which in our case they wouldn't, these would be tied together. I'd take both of these and I'd loop them around and hook them back up here. Right? So I can hide this back up in here behind the wall, and nobody would ever even know it was there. Okay? So then this wire right here, this one that comes out that feeds this contactor and the way I had it wired is this 12 volt lead comes out, goes through the contactor, and then trips the final leg. Abandon this, get rid of this completely, take it out of line, okay, and have it referenced to ground, just like the rest of these. So click, 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 now we got enough amperage, it's regulated, the voltage is going to stay up. All of our problems are solved. It works exactly the way it should with our 1-wire lead system, or hear me out, I changed this a little bit. Anybody that's been following me for any amount of time, I'm a firm believer in the soft start circuit and its need to be in the system, okay? If I take a timer circuit and I add it somewhere in here, I don't know if it'd fit here. I got to make sure that the breaker will clear the timer. But let's say I sneak this timer down in here and I set it for, I don't know, 3 seconds, 4 seconds. I grab the 220 coming off of these contactors and I run it down to the timer. When this first contactor closes, so I stick with the same 25 ohm resistor. When this first set of contactors closes, it trips this timer, and then I have another 2 resistors in line, one to power this and one to power that. Okay. This will trip this contactor 3 or 4 seconds later, and that in turn drives this contactor. In theory, we don't even need to do that. We can completely remove this contactor out of the equation, take our 12 volt lead, run it down to this timer, and then have the timer in turn push this contactor. The problem with that is if we have a short or anything that arcs over in the RF deck or in the high voltage supply, it can run back and wipe the contactor out. That's why we'd use this second one to trip it independently, and this would not be in the positive circuit at all for anything. So, I mean, really, because we didn't have regulators that were like this. I mean, they had DC to DC rectifiers, but they were huge. And I could hide this back up in here, right? Add my little timer someplace, hide it back in here someplace, probably put it on the back side of the cabinet, add a couple wires to this thing, and when I push this button on the RF deck, it turns the amplifier on, click, and then when I decide to fire up voltage, when it sees the signal come in for the 35 volts positive from the RF deck, that starts our high voltage sequence. Clack. So red button controls this, and then everything else is on a timer. This would be easy to do. This is way easier and less invasive because I can hide it back here. I can literally take the input wire and hook it up to here, the output wire that's already in play, hook it up to here, give us 2 grounds, and all I got to do is drill 2 holes in the cabinet to mount this thing to. And then all of this will work just the way it's supposed to with a regulated supply, and we're not worried about a resistor and the voltage dipping up and down a bunch. But then that doesn't address our soft start issue. I like to have at least 1 or 2 seconds where that resistor is taking 100% of the load and those caps are slowly getting filled up. That incredibly increases the lifetime of the capacitor. But at the end of the day, I want to do it with a resistor because that's the way it was originally built. The schematic is a good guideline, but this thing departs from the schematic because the way this is wired, the color code on the wires is all right, the length on the wires is all right. I only have 1 wire that's bringing voltage to this contactor or anywhere up here. But I don't know what else has been changed. There's a red and white wire that was here, but it was cut off and then taped off, and then it ran back to where this white wire hooks up. And I think the red and white wire come around, and I think it burned up. I think this AC mains light burned up, all when he shorted out the breaker to the bottom of this contactor. I don't know. This is the easiest fix. This is the easiest fix. And maybe the time that it takes the electrons to spool up in the coil of this contactor and it closes, and then let's say 100 milliseconds or 50 milliseconds later, when the current spools up in this contactor and it pulls it shut, and then the electrons can rush and spool up in the coil of this contactor and it shuts and it bypasses the soft start, maybe that 150 milliseconds is enough. Because all the evidence is pointing towards that's how it was wired. I just can't. With the same valued resistor, this is a 25 ohm, same exact valued resistor, right? I keep having to drop the resistance lower and lower and lower and lower to where the voltage on this first contactor is getting higher and higher and higher, and it's not regulated, so the voltage is going. Yeah, that's my dilemma. Okay, let's do the sketchy bit. Now I've got half of the 220 phase isolated through my variac. I got a big giant 220 variac that I could plug the whole amp into and slowly bring the amp up and bring it down. I don't need that for this test. So we've got, through the contactors, one of the 220 legs already hooked up. Probably that one. No, that one. No, that one. No, nah, that one. That one. One of the 220 legs in the back is hooked up. Then I'm isolating one half of the leg through this variable tap transformer, variac. Okay. Not isolating, but I'm going to control it. So we're going to act like this is kind of like a buck boost transformer, but on one side of the phase. So this is volts going into into plate transformer. This is volts coming out in RF deck. And when we turn this on, we should see around 2000 is volts. All right, so safety glasses, hearing protection, because this is where shit might get a little wild. I doubt it though. I really took my time and triple checked everything. So we'll turn on the variac, contact. So 125 volts going in, so 250. And then coming out, it's 1,987. Over here on the control unit, and I fixed this issue by the way. Over here on the control unit, 2,000 volts present. I think I even figured out the blinker issue. That'd take 2 minutes to fix. Okay, so let's go ahead and we'll slowly run this up. There's 130 volts, there's 1100, and we're on the low tap. It's not fighting me at all. Of course, there's no load on the transformer. There's 200. There's 220, trimming to 220 on the input. Okay, so 3,500 volts, and this is on the low. Switch over and go to the high, 4,700 volts. It's a little under volted. Back to low. We'll wind this on up the rest of the way. $240 volts. Floating. 3,900 volts switching, please don't blow up. 5,000 volts. All right, let's grab the FLIR. Well, this is up and running. The only thing that should be getting hot is the bleeders, and that's exactly correct. Swing choke's not getting hot. I mean, bleeders are getting really hot, 240 degrees. Make sure they're wired properly. I think they, oh, I know they are. I checked them like 3 times, but. All right, so we're stable. We don't have any leakage. Let's go ahead and we'll run this on down. Shut the variac off. Gotta quick the bleeders are a bit, pulling the voltage out of this thing. That's crazy. Well, success. We have success. That means all of the wiring I did down here, all the high voltage stuff I changed around and cleaned up and replaced with new wire is all working. Both of these caps, even though they were tested and high potted, they're both working in circuit. All the bleeders are working. The plate transformer is working. The swing choke is working. The vacuum relay is wiring in properly, and coming up here to the RF deck, we have the proper amount of voltage. Yes. Yes, sir. Here's a question I've always had. So I had the tap set on the 250 volt tap for our first test, our lowest voltage that we can achieve on our secondary, or on the primary side from the secondary. So the primary side I had set at the 250 volt tap, so runs great at 240. I've always been interested to see what would happen if we go to 230. The primary limiting factor is the oil filled capacitors, which are 8,000 volts each. And they're only 6 microfarads a piece, but it's okay. They're in series, so it's okay, right? So we'll start out on the low voltage setting. So we've got 116 volts going in, roughly, right? And our output voltage once again. So let's go ahead, we'll run this on up. So now let's switch over to the high tap. See, we're already at 4,000 volts. We're only at 160 going in. So we'll go ahead, we'll bring this on up. And under load, you want the tube to sit at about 5,200 volts. That's fully loaded, by the way, not resting voltage. People get that backwards all the time. So at 200 volts going in, 5,200 volts coming out, 5,000, almost 6,000 volts displayed. So we'll go on up, we'll go to 210, we're at 5,500. And 20 volts, 5,760 volts without loads. That means it probably fall down to about 48 and some change, or yeah, 48, 49. My wall voltage is 235 at 5,900 volts. It actually looks all pretty good. Yeah. Put a little bit more step in its pep, I think. Let's go, we'll back this off. Shut this off. We'll shut this off. So what do we have for line voltage going in one more time? Did our leads come off in the back? What happened here? Let's walk around to the danger zone. Highway to the danger zone. Okay, so I want to show you this. Without the soft start circuit that I'm going to probably put in it tomorrow, and me just putting a voltage regulator in there, because I covered that. I didn't show what I did. I actually put that little voltage regulator in there, so now everything's getting a nice 12 volts. Everything's locking up and latching the way it should. It doesn't show on the analog meter, but because the analog meter's too busy, or the digital meter's too busy counting, but it shows here on the analog. Watch this as this goes through its startup procedure. See how it hops up to about here and then it lurches forward? You can hear there's a click and then a click. That's the soft start. That's what they designed. Huh. Now we're going to slow that down. I'm going to slow that down just so I can sleep better at night myself. Yep. So now, put the hearing protectors back on. Let's try this at full start power. So we've got the variac in line, we got the variac turned up. Okay. Works for them. Fair enough. Wow, fair enough. Okay, so the things I got left that I want to play with now that I've figured this out, which was I had to move a ground, is the 10 meter / 11 meter switch position, how that works, and then a thing called the blink indicator. I'll show you what I mean here in just a second. Let me reset, disconnect some things, make myself safe again, and we'll try something different here.